now because I'm kind of busy, but I'm very happy to help you. Otherwise, we are going to surrender before we fight the war. Learning or the spirit of coming to NUS. To put your comments. Yeah. Oh, put already. Oh, thank you. Because some people cannot find it. Like Liao Xue cannot find for a long time. Like that. You take that machine learning class, right? Is it completely online? Oh, really? Yeah. Oh, that's different. When I taught the tutorials, it was all online. Okay. Do you remember the name? Man or woman? Guy. Oh. China guy. Okay. All my tutorials are recorded, and I think they are pretty good quality. All my tutorials for the EE20 Or is it 2211? They are recorded somewhere. Hello, can the people in Zoom hear me? Come on, why are there so few people here? Oh, it's raining today. Can the people in Zoom hear me? Please say something. Wicked, why are you not here? Okay, very good. Oh, no. If Oliver stays in Utown today, then there will be no one to accompany me here, right? Okay, please ask any questions you want to ask. And today we are going to go through some parts of section 4.1, but we will then also comment on section 4.2. Right, so we recall that if x and y are independent with PDFs, fx and fy respectively, then we are interested in the sum. And we are interested in the PDF of the sum. The sum is z, and the PDF has a certain form. All right, you don't need to know how to prove this, but you need to know how to use this. All right, and this sum is called the convolution of fx and fy. Okay, so we have done several examples, but now we will do another example that is a little bit unconventional. This is also in the book. Example. Okay, so we are going to find the PDF of x minus y, where x and y are independent random variables, independent exponential random variables with rate lambda. Okay, so that particularly means that fx of x is equal to lambda e to the minus lambda x for x bigger than 0 and 0 otherwise, and same for y. So fx has the same distribution as fy. Okay, so it's important that they are independent, otherwise we cannot use the formula. Hello, want to join? So what we have done, right, is we have established last time a particular formula that you ought to commit to memory. There are not many things in life that you have to commit to memory, but this one formula is something that you have to, even after you leave NUS. Okay, this is one important formula. But as you can see here, there's an issue, because now we want to derive the PDF of x minus y, but we have x plus y. So how? Do we just give up? No, we cannot. As I always tell Oliver, we cannot give up. So we need to know how to use it, how to use the formula in the right way. So we can we can consider using the formula on x plus the random variable minus y. Okay, so we can think of a particular random variable. We have x, which is this guy, but minus y we don't have. Okay, so nevertheless, let us draw a picture. So x has a particular exponential random variable form. So its PDF looks like the following. This is fx of x, and the PDF is actually 0 on the left-hand side, and then it grows to this, and it decays like the following. And this curve here is lambda e to the minus lambda x. So that is the PDF of x. All right. So now, if we want to use this particular decomposition of z, where y is minus y, then we have got to figure out what is the density of minus y. What we do have is the density of y. Density means probability density function. The density of y is exactly the same as that of x. This is fyy. Okay, and it has this same shape as x because they are identically distributed. Okay, so fyy is the following. So it has the same distribution, lambda e to the minus lambda y. Of course, on this side is 0. So we don't need to talk too much about that. Now, if we want to use the formula in the big box here, then we need to create the density of minus y. So maybe we can call that something, but we don't have to call it anything. Let's call it, okay, if we want to, we can call it w equals to minus y, the random variable. So now we need to be able to figure out the density of w. Okay, so the density of w looks like this. Okay, so this is fw of w and it is flipped, all right? Because whatever the value of y, it has this particular value, then w will have the negative value. So it is over on the other side and it grows exponentially fast up to a certain point. This point is lambda. This point is lambda, and then it drops down to 0. So this is the flipped version of the y density. Okay, so that is fw. Actually, we can call this, if we want, f of minus y of w. So now our job, right, is to then, what is our job? Is to convolve these two densities. This is lambda e to the lambda w, it grows. Okay, so our job is to then convolve these two guys. So what is the meaning of convolve? Convolve means we flip and then we slide it left and right. Okay, in signals and systems, you are electrical engineering. In signals and systems, EE20 something something, you'll learn this, if you recall. So I'm just reiterating this. So now we need to flip and then we need to slide. Okay, so once we flip this, we need to flip this and then we need to slide. We flip this, we get back here. Then we need to slide this left and right. Okay, so now we are going to implement the formula given by convolution. So we want fz of z, which is minus infinity to infinity fx of x. Now this is fy, okay, but now we are in the business of z equals to x plus minus y. So this should be the density f of minus y, z minus x dx. Okay, but this one here, okay, f of minus y, note that f of minus y of y is equal to, so this f of w, if you wish, is exactly equal to f of y of minus y. Because this is the flip version. So you need to flip the argument when you flip the random variable. Hence, at this point, it's f of y of what? X minus z dx. Okay, so this is some interesting change here. Right, so now we need to figure out what is the overlap between this and that. Okay, so let's sketch this for z positive first. So let's focus on this formula. Z positive, and then maybe non-negative if you wish. Then how does it look like? How does this look like? Okay, so we are going to now copy this, all right? Okay, because we want to be able to draw this. Okay, so we have this picture here. We are going to slide it very soon. And we have this picture here, the original density of X. Okay, and we're going to assess the amount of overlap very, very shortly. Okay, so now what we are going to do is we are going to redraw this. Okay, for a positive Z. All right. Now you have to follow this a little bit closely because this is also useful for your signals and systems if you are electrical engineering person. Okay, f of y of, okay, let me get rid of this, of what? Okay, this is the x-axis of x minus z. Okay, how is this drawn? Okay, now notice that z is positive. So this whole graph here gets shifted to the right by z units because of minus z. Why is that so? When z takes on the value of 0, we are here. When z takes on the, say, the value of 1, we are have fy of x minus 1. This is a translation of the graph to the right-hand side, okay, which is a little bit counterintuitive. So we are actually like this. This point is lambda, and this is fixed, and this goes down like this. And the equation here is actually lambda e to the minus lambda x minus z. Okay, well, the original equation for fyy is equal to e to the minus, okay, maybe there's a lambda here, lambda e to the minus lambda y. So when you want to do x minus z, you basically plug the x minus z into here, and that's why you get this. Okay, so this point is exactly z. Okay, so now everyone understand this. This is absolutely crucial. Everyone understand this? Wee Kiat, you understand this picture? Very good. So we have now got to ask ourselves, where in the world is the overlap? When you multiply these two guys together, where is the zero part? Well, the zero part is certainly left-hand side because 0 multiplied by 0 is still 0. Here, from 0 to z, this person is 0. So no matter what this guy does from 0 to z, it is immaterial. And so this integral here goes from z all the way to infinity. Because anything less than z is truncated by this effect here. This effect here, this part in particular. Understand? You multiply these two graphs together. You just imagine in your head, where is the zero part? It's from infinity, minus infinity, all the way to z. So the non-zero part is only this part here. Where is my friend Valencia? Is she here? Maybe escaped. But if she were here, I will ask her. So now we are in the business of putting everything together. Lambda e to the minus lambda x and lambda e to the minus lambda x minus z dx. Understand? Oliver, understand? We move this to the right. We multiply these two. There are a lot of zeros. Okay? Here, all 0. All right? All the way here up to the value z here, all 0. That's why the only non-zero part is from z all the way to infinity here. All the way to infinity here. This constitutes this. Okay? Shifting to the right-hand side of the fy. Okay? So now, once we know this, this is a direct integration, but there are a lot of things that are constant. Lambda squared e to the how many? E to the plus lambda z. Okay, am I correct? Yeah, e to the plus lambda z, integrate from z to infinity, e to the minus 2 lambda x dx. Okay, so now I'm not going to teach people how to integrate, but if you're interested, you go and work this out by yourself. After you're all said and done, you have lambda over 2 e to the minus lambda z. This is for z greater than 0. For z less than 0, we have a different story altogether, which I will do in a short while, like now. Everyone understand this? Everyone understand? Alvin Chi, you understand? You often come to my tutorials, but how come never show up here? Alvin Chi, great. Okay, so now we will move on to z less than 0, which will illustrate another point. So this guy stays the same because it is always the same inside the integral. Always the same. But the y part is now different. Okay? And I want to highlight that this is no longer 0 here. Okay, so we just keep it simple. Okay? Now the y, if z is negative, then the graphs get shifted to the left-hand side. Okay? That is our fy of x minus z, but z is a negative number. So now the red graphs get shifted to this side here, like this, and here, and z is a negative number, it is here. All right, this is the lambda height, and we have this exponentially decaying behavior here. And now this graph here takes the form lambda e to the minus lambda x minus z. Then we ask ourselves the question, right? What is the question we want to ask ourselves now? At this point, we want to implement what formula? We want to implement this particular formula, right? We want to implement this. So not the whole world is positive. The whole world is not positive. So the next thing we want to do is to implement a certain reduction. Okay, we want to put the limits here. So can someone tell me what are the limits to put? No. Yes or no? No. Come on, anyone else? We want to multiply these two guys together to see where is the positive part, the non-zero part. You multiply these two things in your head. You go point by point. Okay, Oliver said minus infinity to z. Yes, indeed, that is all 0 because of on this side also 0. But how about from z to 0 here? Well, this guy is positive, but this guy is still 0. So 0 multiplied by something positive is still 0. Now, what about from 0 all the way to infinity? Both guys are positive, so they are positive. The product is positive. So this limit here goes from 0 to infinity. Understand? Okay, so now the rest is just mechanical. We have this thing here. Okay, all these are the same because the integrand is the same. Integrand is the thing inside the integral. This one is the same. Okay, but now we need to adjust this because Oliver and I agreed that the limits are here. And then what we have here is correct or not? Right, so hopefully this is correct. Lambda over 2 e to the lambda z. So now what we have, this is for z less than 0. So in summary, we have that the convolution, okay, is the following. Lambda over 2 e to the minus lambda z for z bigger than 0. Minus lambda z for z, and for z less than 0, we have something symmetric, but here is plus lambda z. And this looks like the following beautiful shape. Now the book has a different way of doing the left-hand part, but it's too quick. Okay, it looks like this. Okay, this is not going to go to 0. It's here. This is lambda over 2, and it's this symmetric thing. So we have evaluated the convolution, and it looks exactly like this. That is your f of. That is exactly your f of z evaluated at z. Does this make sense? Alvin Chi, does this make sense? Okay, Sawiket and the previous person who I cannot see, they are all wrong. Alvin Chi, Long Tengjie also not right. It's from 0 to infinity. Everyone understand? This is really crucial, and I'm going to draw this. Okay, the only non-zero overlap is from here to infinity. From here to infinity. Understand? Everyone here understand the orange part? Okay, because for the other part, you are all 0, right? Say this part here, the blue part is all 0, 0, 0. Because at least one of the functions is identically 0 there. Okay? So all these answers here are not quite correct. We have to do careful bookkeeping. And so after we have done this correctly, you see that these are the limits here, and they are absolutely crucial for us to integrate this properly. And I'm not carrying out this integration. You do it and verify that it's correct. Okay. Actually, I have one more example to go through, but if we have time at the very end, I will go through. I want to go to talk about covariance and correlation first. Can I continue? Alvin Chi, can I continue? Sorry, I only know a few people by their face, so I have to. Okay, go ahead. Very good. All right, so now I want to talk about section 4.2. Let's start this new section. And this is not very difficult. I don't think this is as difficult as convolution or derived densities or derived distributions. If we have time at the very end, we will do another example of derived distributions taken from the tutorial. Okay, so covariance and correlation. Well, this is a very important concept in statistics. You will encounter that. So we want to understand, for example, right? Does this batch of students have anything to do with the quality of the instructor? If the instructor is good, like myself, then do the students do better in the exam? That is some form of correlation. Okay, that's why this is important, because we want to understand whether the instructor has any effect on the students or we are completely independent. All right, no matter how good I teach, you will only perform as your level. All right, so let's do a definition. The covariance between any two random variables. This is the technical term covariance of two random variables. Actually, you have seen it in some homework before. X and Y. Now, the random variables could be discrete or continuous. This is denoted by COV. XY is defined as the following. It is an expectation of some random variable. X minus expectation value of X, Y minus expectation value of Y. Okay, notice that this guy here is a random variable. You are taking away the mean from a random variable. It is still a random variable. It is a zero mean random variable. This guy is zero mean. This guy is also zero mean. You multiply these two random variables together, you get a new random variable. and you take its expectation. Now, this guy is a zero mean random variable. This guy is a zero mean random variable. You multiply these two guys together. Generally, that need not be zero mean. And so this may be some number. This may be 5. Okay, maybe some number. So we want to try to understand what is the meaning and implications of this number shortly. Okay, now when the covariance turns out to be equal to 0, then there is a technical term for this. We say that x and y are uncorrelated. Okay, so that is a technical term for the fact that x and y are uncorrelated. Okay, now you want to have these pictures in your head. All right, so if the correlation, or sorry, the covariance is positive, means that, okay, x has a positive influence on y. So I have a positive influence on you. If I teach well, then you do better in the exam. All right, so this is x and that is y, and the shape generally looks like this. Okay, there is a positive correlation. Now, in some cases, however, I have a negative influence on you. So x and y are negatively correlated. And what does that mean? That means that the mass of x and y in this two-dimensional plane looks something like this instead. All right, when x is large, y tends to be small. Okay, so that is the situation when covariance xy is negative. All right, so in English terms, so if x is large, y also tends to be large here on this side. Now, of course, on the other side, if y is large, then x tends to be small. Okay, so that is the meaning of, that is the intuitive meaning of the covariance. Tends to be small. Okay, so that is the intuitive meaning, but of course we can calculate the mathematical covariance in a proper way. But here's a very nice property before we do an example. All right, so property. So the covariance of x and y is given by this formula that you should also commit to memory because it's very useful. Okay, now this formula is not so convenient. Actually, the property is that this can be written as this is called a correlation. Expectation value of xy is called a correlation, minus the expectation value of x times the expectation value of y. Okay, so this is a claim. This requires a small little justification. I don't want to call it a proof, but it's a simple justification. So let's prove this. Okay, so basically, this is actually difficult to evaluate in practice. We usually use this formula, just like the variance, we define it to be expectation value of x minus expectation value of x quantity squared. This is the vanilla definition of variance. But I showed you before that this is expectation value of x squared. This is called the second moment, minus the expectation value of x quantity squared. So the second formula is what you actually implement in practice, because it's usually easy to compute the first moment and the second moment. All right, you don't want to compute this one. It's troublesome. Okay, but nevertheless, what we have here, the claim here is that the covariance also has the same property. And so we will prove this using a few simple steps that are not very scary. All right, so we start off with this. We start off with this, and so we can expand the square. All right, it's just like a minus b, c minus d. Okay, this is ac minus bd. I don't know how to do this. AD minus BC plus BD. That's what we are using, okay? But let me get rid of this. And that's what we are using here. So we have XY minus expectation value of Y minus Y expectation value of X plus the product expectation value of Y, like this. Now, because expectation is linear, this one can go inside. So we have the correlation. This immediately recovers this part here. So the rest must be the rest. Okay. So we must make sure that the rest is the rest. Okay. So this is minus expectation value of X, expectation value of Y, minus expectation value of Y, expectation value of X, and plus the expectation value of the inside, the product Okay, but what do we notice? This we keep because we love it, all right? But now this is a number. This is nothing but a number. It's just an expectation value of 3x. It's 3 expectation value of x. The constant can be brought outside. So that's exactly what we'll do. Expectation value of y, expectation value of x. Then here, what we have is that this is a constant, it can be brought outside. So now we have the same thing, expectation value of y, expectation value of x. But now this is nothing but a constant. You don't need to take its expectation. So we can just extract this guy here and put it here. But now we notice that there are extra copies. All right, this copy here and this copy here are the same thing. And so what we are left with is exactly what we are seeking, which is exactly the first 2 terms, and that completes the proof or justification. This is what we will use to compute the covariance and not any other complicated formula, because this just involves the expectation of the 2 random variables as well as the expectation value of the product. Okay, does anyone have any questions on this simple derivation? Nope. Okay, the thing you need to know is that this is a constant. And so it can be brought outside. Okay, and this is a constant as well. So the expectation operator can be ignored. Okay, so this is also a constant. So this whole thing can be brought outside and our life simplifies. We have 2 cancellations here. Okay, right. So now there are a few other properties of the covariance that are useful, and I'll just list them without proof. Properties. Now, the covariance is obviously related to the variance. Suppose we have the covariance of x and x. The claim is that this is the variance of x. This can be verified by the formula itself. Okay, let me just do a small verification here, right? Because this guy, covariance of x and x, is nothing but the expectation value of x times x minus the expectation value of x squared. And this comes exactly from this simplification here. Can you see that? So I just plug y equals to x here. Just plug y equals to x. Now, we have the second moment minus the first moment, quantity squared. And this is exactly the variance. So that's the justification. All right, that's property 1. Property 2 says that if you have the covariance of x and ay plus b, so y gets transformed to ay plus b, then this is going to be A of covariance of x and y. Notice the following, very important, right? The A gets outside by 1 copy only, 1 copy only. This is different from variance. All right, I will remind you of the variance shortly. And furthermore, this shift here disappears. It disappears. The right-hand side has no this shift. Okay, this is similar to variance. Now we recall a similar property for variance. The variance of say ay, maybe ay plus b. What is this? This is a squared variance of y. So again, the shift does nothing. The shift gets killed. But the a, notice, we have this property that it must become a squared. Okay? So this one you have used before. The covariance you have not used before. So this covariance is slight generalization. If I adjust this by a scalar a, here a and b are some scalars, fixed scalars. A, b are some scalars. They are real numbers. Okay? Then if we multiply the y by some fixed number, you multiply the covariance by the fixed number. Okay? The shift makes no difference because why? We are always subtracting the mean. All right. So that's the second property. You can show it by yourself. So now we also have the third property, covariance of x and y plus z. That is nothing but covariance of x and y plus covariance of x and z. And there, no independence is assumed here. This is okay without any independence. No independence of x, y, z is assumed here. So all these are properties that you can actually justify by the definition of the covariance itself. Okay. Now here's another property for if indeed X and Y are independent. All right, that is a very nice situation. Then the covariance of XY is equal to 0. Okay, we always have this. And why is that the case? I will explain this. I will show this in more detail. Why? Because the covariance of X and Y we have shown is the expectation value of XY minus the expectation value of X, the expectation value of Y in the simplified formula. Now, if they are independent, the expectation of the product is the product of the expectations. This is where independence comes into play. And we have this subtraction term here as well, right? And here we are using independence in a big way because X independent of Y implies that expectation value of XY is equal to expectation value of X multiplied by expectation value of Y. And so after we are all said and done, this is equal to 0. So this is a justification of the fact that if X and Y are independent, the covariance must be 0. So Oliver, you must remember this for life. Okay? However, another thing that you should remember for life is that you cannot go backwards. All right, if you notice that the covariance is equal to 0, can you conclude X independent of Y? No, as the following example shows. Okay, so this example is a very neat example. Actually, you have also done something similar in the homework too, all right, which Oliver found a bit difficult, but nevertheless, I helped him. So this example says the following. All right, we have 4 mass points and they are at 1, 0, 0, 1, 0, minus 1, and this point. So this is 0, minus 1, 1, 0, 0, 1, and minus 1, 0. And we have a uniform distribution, and the weights are all 1 quarter, 1 quarter, 1 quarter. And this is our X, this is our Y. So in particular, if I were to write this down, we have Pxy, our probability mass function. This is equal to 1 quarter if Xy is equal to 0, 1, or Xy is equal to 1, 0, or Xy is equal to minus 1, 0, or Xy is equal to 0, minus 1, and 0 otherwise. Okay, so these are the only 4 choices. Now, let us evaluate the covariance of X and Y, and let's justify that this is equal to 0. Now, this is very ugly. Equally ugly, but I don't know how to make this nice. All right, so now let's compute the covariance of X and Y. Now, we use the simplified formula XY minus expectation value of X, expectation value of Y. Okay, so right from the picture, you can already see what is the expectation value of X. Okay, how to see that? How to see that? You see, this whole thing is symmetrical, right? This whole thing, this probability mass function is symmetrical. So we are now looking at the expectation value of X. All right. So we're going to see. Well, let's do it slowly. Okay. Let's find the marginal density, marginal PMF of X. So P of XX. All right. X can only take on 3 values: -1, 0, or 1. Okay, so we can actually draw it. Okay, so here we have half at 0. And I'm going to explain why it's half. 1 quarter at -1 and 1 quarter at 1. Okay, why is that so? Now you look at X taking on the value 0. You have to add up this mass point and this mass point, and this gives you half. You look at X being equal to 1. So you focus on this strip here. All right. The only mass point that it picks up has mass 1/4. And similarly for the left-hand side. So now we ask ourselves the question, where should we put our wedge so that this is balanced? We should clearly put it at 0. So the expectation of x is certainly equal to 0. Okay, by symmetry or by deriving the probability mass function of y, we have that the expectation value of y is also 0. Is this clear? Is this clear from the picture? All right, let me ask the students here. Valencia, you're here. All right, do you understand this? Do you understand what I've drawn here? You first find the PMF of x. You look here, here, here. You're adding up the mass points. So in particular, this mass point gets transferred here, and then this mass point gets transferred here, and then these two mass points get lumped here together. Understand? All right. So the wedge, if you put it here, becomes balanced, and so you have expectation value of x equals to 0. All right. So now what we are going to do is to figure out the expectation value of xy. Now we can use the formula. You sum over all possible values of x and y, xy, pxy, xy. That is the formula for the correlation. This is called the correlation. Okay. You look at this. Immediately, you look at it and you see that it's 0. Why is that so? Does anyone have any idea? There's no need to do anything. Actually, I have a friend here called David, right? How come he's not here today? Is David here? No. Oh, how surprising. All right, never mind. Let me ask Sean. Sean, what is this thing here? And why is this thing what you say it is? Sean. I'm not sure. No problem. Does anyone want to help Sean? Huh? Yeah, the expectation value of x is 0, but that says nothing about the expectation value of x and y, x times y, right? No, no one says that it's independent. Yeah, Soviket, thank you very much, very fast. Soviket says it's 0, and the reason he provides is also correct. Now, if you look at this particular formula here, right, you have to always do the product of x and y, multiply x and y together. Now, you go to this picture here. Every mass point, you multiply x and y, you get 0, because at least one of the x or y is 0. You don't believe me? Here, you take x, which is 1, and y, which is 0. You multiply these two together. Okay. Multiply these two numbers together, you get 0. These two numbers you multiply together because there's at least one 0. So it's 0. These two numbers, there's at least one 0 here. So it's 0. So this term here is identically 0 for all the terms. So no matter what this number is, it is 0. Okay. Does this make sense? Sean, do you understand this? Okay. If you don't believe me, let us write this out in full. All right. So you have 1 times 0 times a quarter plus 0 times 1 times a quarter plus 0 times minus 1 times a quarter. Here we're doing it very slowly. Minus 1 times 0 times a quarter. So that is 0. Sean, understand? I'm taking care of all the mass points here. Very good. So since everything is equal to 0, covariance is equal to 0. Because of this particular formula, it comes from here. All the terms here are 0. So there's nothing much to say. This is 0. Does everyone understand this calculation? Oliver, you understand this calculation? Okay, no problem. We are going to use this formula. All right, we're going to use this formula. In order for us to use this formula, we need to figure out 3 things. 3 things. We need to figure out this term, and this term. Now, in order to figure out this term, you either look at this picture and argue by symmetry, or you go and figure out what is the probability mass function, which is this, because Valencia agrees with me. But here, this probability mass function, by symmetry, the expectation value is 0. So this is equal to 0. We don't even need to worry about this. Okay? Now, so we need to figure out this, which is the most difficult thing. All right? But Soviket says it's 0. And why is it 0? It's because of this calculation here. And this is because there's a product of x and y here. Every point here, the product of x and y is 0. 0 times 1, 0. Minus 1 times 0 is still 0. So I wrote out the explicit expression here. And each one of these terms has a 0. So the expectation value of xy is identically equal to 0. And we plug this equal to 0 and this equal to 0, we get 0 here. Understand? Oliver, I explained this 2 times already. No? You just evaluate the 3 terms. Okay? Go back and think about it. Don't understand, still can ask me. Okay? The problem here is the following. I want to make the point, so the covariance is 0. However, are the random variables X and Y independent? Now, there was a student up there who unfortunately thought that the random variables are independent, and so this one decomposes, he thinks, to this. But this is not true. The answer here is no. We don't need to do too much work to determine that they are not independent. Why? Because if I know that X is not equal to 0, then I know that Y must be equal to 0. Why is that so? Let us look at this picture again, and I'm going to break it down for convenience of everybody. Oh, sorry. Let me bring this picture down. So, independence means that if I give you information about something, you don't know anything about something else. So if I tell you whether or not it's raining now, it does not affect my performance in the exam. Maybe that's not true, but that's the meaning of independence. All right. So now if I tell you, however, that X is not equal to 0. So X is not equal to 0 means, okay, X is not equal to 0. All right. Is the situation that X is that we are either here or here. There are only 2 choices. X is not equal to 0. It must be plus or minus 1. It cannot be the center. And so we must know that the coordinate of Y is definitely equal to 0. Here, this coordinate 0, this coordinate must be 0. So if I know that I have some partial information about X, I have a lot of information about Y. That means that X and Y are far from independent. They are not independent. Okay? This implies that X is not independent of Y. Of course, you can do the hard work and you can check that P of XY is actually not equal to P of X times P of Y. You can check this, but this takes effort and we don't actually need to do that. Okay? So we're not going to do this. We're just going to observe by picture that if I know that X is not equal to 0, so I have partial information about X, I have information about X, I can actually know something about Y. Okay, that means that they are not independent. Understand? Right? So we are in this particular situation. Right? This situation is this situation. We are here and we are here. And we have some information about Y. Must be 0. Okay? Understand? Yes, must be 0. Because if X is not equal to 0, we are at the sides. That means Y must be equal to 0. Okay? Huh? The point here is that if X is not equal to 0, then Y must be equal to 0 from the picture, right? Because if X is not equal to 0, we are either here or there. So Y must be equal to 0. Y, we are on the horizontal axis. Okay? Right. I want to now go through some other simple concepts. Okay, I have only 1 page left. And that concept is called the correlation coefficient. Okay, the correlation coefficient is a normalized version of the covariance. Covariance can be 100, it can be very big, but the correlation coefficient is some normalized version. The correlation coefficient is given the notation rho xy of 2 random variables x and y that have positive variances. The book says non-zero, but it's positive, okay? Variances is given by the formula rho xy is equal to covariance of xy divided by square root of the variance of x, variance of y. So that is the form. There's a certain formula that hopefully you commit to memory. Okay, so there's a formula. Now it holds that, and the book actually shows it in the exercises that I'm not going to do. It holds that rho, let's start with just write rho. Rho is at most 1. Okay, what this means is that rho is between -1 and 1. So there's some normalized form of the correlation of the covariance. Covariance can be 100, but 100 is not a meaningful number. Just like, okay, I tell you that you got 99, or you got 95 in the exam. Is that a good score? Maybe not. Because what if everybody got 99? Then you are the worst, right? So this is a normalized version of the covariance. All right, covariance can be super large, can be super small. You cannot really tell whether the random variables are really correlated or not, strongly correlated or not. All right, but because we are dividing by the variances here, we are normalizing. Then we can say that, okay, in fact, we are very correlated or very not correlated because of this normalization from -1 to 1. Okay, so in particular, all right, if rho is equal to 1, we call this positively correlated, completely positively correlated. I'm making up this term. Positively correlated. Okay, this is completely positively correlated. Then there exists, this is a math thing, a constant C bigger than 0 such that x minus expectation value of x equals to C y minus expectation value of y. So they are completely positively correlated. Okay? Right. So let's do a particular, you can also do the same for completely negatively correlated. Okay? So we can do the same thing if we want. If rho is exactly equal to -1, then we are completely negatively correlated. Negatively correlated, then exists a constant C less than 0 such that the same equation holds. Okay? Now, this can also be thought of as Euclidean geometry. Okay? So it's a bit abstract, but random variables can actually also be thought of as vectors. All right, I think it's too abstract, but roughly speaking, if rho is equal to 1, you have two vectors that are pointing in the same direction. This actually says that these two vectors are pointing in the same direction. There's a C. They may be of different lengths, but they are pointing in the same direction. This is too abstract. Okay, but let's do an example to make this more concrete. Okay, final example. Now we are going to toss a coin n times. N independent tosses of a coin with bias P. Bias means the probability of heads is P. Okay. So let X be equal to the number of heads in the n tosses. And we are going to let Y, of course, not be so surprising. Y is the number of tails in the n tosses. Y is the number of tails in the n tosses. Now, clearly, X plus Y must be equal to what? Oliver, simple question. We have a coin can only be heads or tails. X is the number of heads, Y is the number of tails. And suppose I toss a coin 10 times. The total of heads plus the total of tails must be 10, right? Logic. So, no, that is on expectation. That is on average is half n, but then you could be very lucky or unlucky and get all 10 heads, right? No one is discounting that. You could get 10 heads, you could get 10 tails. But the sum of the heads and the tails must be equal to 10, right? What is also true is that you can take expectation value on both sides. Expectation value of X plus expectation value of Y is equal to n. No problem. Term J is correct. So what we have by combining these two equations, we take equation 1 minus equation 2. We get X minus expectation. We get X minus expectation value of X is equal to minus. Actually, we subtract, okay? But whatever we do, it holds that this is true. Okay? Because why is that so? Because you x and y you add together is the same as you add this expectation and this. So this is just some bookkeeping. Okay, I'm not going to talk too much about this. This equation holds. Okay, because x plus y is n, expectation value of x plus expectation value of y is n. Okay, so what is the covariance of x and y? What do you think? Now, before we do anything, let us try to understand. Can we guess the covariance or the correlation coefficient? Now, if you have a lot of heads, you will have very few tails. If you have very few tails, you have a lot of heads. They seem to be negatively correlated. In fact, they are completely negatively correlated per the definition here. Completely negatively correlated. This is believable, right? Because if you have a lot of heads, we're going to have very few tails. Let's see whether when we plug into the formula, we get what we want. So the correlation coefficient between x and y is, we are expecting it to be -1. Let's show that it is -1. Okay, because we are expecting it to be -1. Let rho xy, the formula is covariance of x and y divided by the square root of the variance of x and the variance of y. That is the formula. Okay. Now let's compute the numerator first, covariance of xy. That is nothing but expectation value of x minus expectation value of x, y minus expectation value of y. Okay, that's the formula. But now you notice that, okay, what do we want to do? This guy is minus of this guy here. Okay, so we have expectation value of x minus expectation value of x. Okay, y minus expectation value of y is minus x minus expectation value of x. Okay, because of this relationship here, this guy here equals to this, then we have that this is equal to, you have to have the minus sign here and this. So I'm just plugging things in. It's not very exciting. So you have minus of expectation value of x minus expectation value of x, quantity squared. And this is defined to be the variance of x. Okay? Now, by the same token, you can show that the covariance of xy is equal to minus the variance of y by the same way. I'm not going to belabor the point. So the correlation coefficient xy is equal to, we're going to plug this in now. Plug this guy here. This guy equals to this. And this, we're going to plug it into the formula here. Just plug it into the formula. And then we'll see some cancellations. Okay. So let's plug minus variance of x divided by variance of x. Now, variance of x is the same as variance of y because they are both equal to the covariance. Variance of x is the same as variance of y because both of them are equal to the covariance. So I can put variance of x here. Okay, but in the bottom, we have the square and square root. So you have variance of x divided by variance of x. And this minus 1. As what we expected it to be. We were expecting it to be -1. And so what we get is -1 as desired. Is this clear? All right, this is where I will stop today. Are there any questions? So today we did a convolution example that was not so easy. Today we went through the definition of covariance and correlation, which I think is not so difficult. And I will see you on Thursday. Hopefully more people will be here. Right? And today the homework is due, so please submit it. Okay? Very good. Okay, so now there are some people who are here who want to ask me questions about homework. You can come down. I have a few more minutes. All right. Okay. Great. Thank you very much, everybody. And I'll see you on Thursday. Hopefully more of you will come. Right. Yes. on. Not the homework. Okay. Yes. Okay.
We use like
Yes, you use linearity. So I help you here. So suppose you have magically found you have found this one.
7C.
Suppose you have found this, so you got this something. Okay, so now we want this. Then this will be something just minus 1 plus x. Because we can split this into two parts, this will be expectation value of y given x equals to x plus expectation value of 1 plus x given x equals to x. But this part here, this is not random. This 1 plus x is not random. So this part here is exactly 1 plus x. Okay, so this will be, let's say we got something here, some number here, is something minus this one. Okay.
The 1 plus x is just a value.
Yeah, just a value. Because this is just a number.
Yeah.
There's nothing random. That's why this is lowercase. Okay. Yeah. Anything else? Okay. So Deng Jie, are you okay? I'm going to shut it off. Okay.
Thanks, Paul.
Sure. Deng, yeah.
I'm curious, what does a value of -1 mean?
That means they are negatively correlated.
Okay.
Completely negatively
So
correlated.
they're going up.
So if we view this in Euclidean space, right? Actually, random variables are in a higher course. Random variables are measurable functions. They are functions actually. Now, so functions have, you can think of them as having as vectors or infinite domain vectors. So random variables can also be thought of as vectors. So what happens here is that you have this particular vector x, this is the origin, and y is pointing in the opposite direction. Y is pointing
totally
opposite direction. All right, so they are completely negatively correlated. This is the origin and this is y.
Okay.
So that means that is the implication of correlation coefficient equals to -1.
Okay.
So roughly speaking, okay, if you generate samples, right, from this particular pair of random variables, now for positively correlated random variables, what would happen is that they will lie on a particular line. This is positively correlated random variable. So you have samples that are lying on this line, positively correlated. Okay, so when you generate samples from this random variable, you will have this positive correlation. This is for c bigger than 0. Now for completely negatively correlated, you will have this situation. All right, whenever x increases, y decreases in a linear fashion.
Okay.
Okay, so this is when rho is equal to -1. This is when rho is equal to +1.
Okay.
Okay. This picture here is a bit similar to a picture that I drew in the beginning, but this is for the case when rho need not be exactly +1. Maybe it's 0.8. Pretty correlated, but it's not fully correlated. It's 0.8. This is maybe -0.8. Okay. Yeah.
Oh, which
question?
the first, this one is take the B1 over the area of the circle. Just count.
Why does this become this so sudden?
I mean, the numbers
Because
are
the
there,
radius
but,
is 4.
I'm not going to draw anything with my finger.
If it's the full circle, the full target.
But then
I don't
this
have
should
a
be
tab
like
over
this
there.
one. This curve, like 1 over r squared.
Then if I differentiate the CDF right that we found in question 1, then I get another answer. I don't know.
I don't know the question. Sorry, I don't know the question.
Like this, the dot is likely to land on every part. So it's one of the
One of the area, yeah, this one is the answer. Yeah, so this is the answer for this one. This one is This one equals to 1, right? It's more than these 4 points, you know. It's the whole circle. Right?
Well, I thought it's the area x squared plus 1 y squared equal to 1 is like
The
area
whole,
of
all the points that x squared plus y squared equal to 1, right? Is the entire circle.
or is the whole probability.
Whole, how to call this, perimeter of the circle has x squared plus y squared equals to 1. Okay. So it's not just these 4 points, if I'm not wrong.
Or as long as like
Yeah.
this 0.
Like for example, here this theta, right? Cosine squared theta plus sine squared theta is 1.
Oh, does that mean we need to bring the polar?
No, you don't need to. I don't think so. I don't think you
I think
need to.
we have it in terms of R. I don't
Yeah.
know why we would need to switch to X.
I also don't know. Yeah, I also don't. I haven't done this, you know. I haven't done this. I know it can be done.
I mean, what I did was I took just left it in terms of R.
Yeah, I think that should be the way.
Because for the PDF of this, it's 1 over our area. Every point, it doesn't specify anything saying that the points are not equally likely. So it would be
We
1
can assume
over-
that, I think.
Yeah,
Otherwise, you cannot do it.
should be 1 over.
Like
our
this,
area.
Let me see. Because I cannot remember.
Yeah.
I've been preparing a lot of other questions.
So for B and C.
We're not sure. if
We
it's
have to
correct,
find.
though.
Okay, I give you a hint, all right?
Okay.
You have to find the. I think you have to find the ratio of the area of the smaller circle in terms of R to the bigger circle. That
Yeah,
is-
because that's the first part
Yeah,
of the answer. So what we thought at first is we can just use 1 minus this answer.
Mhm.
But then this one,
question
the
still
question
use T as a
specify
function.
using the PDF
Yeah.
to find the.
So you find the PDF and then you find the you find the PDF of this one first, and then find the probability that the dart is outside the bullseye. Bullseye is defined as what?
Plus one.
So you have to find. You take 1 minus, huh? 1 minus. You can also do that.
Yeah, but because they say use PDF, so we thought you can't use that.
You can just integrate from 1 to outside the PDF. Integrate from 1 to the 4 of the PDF. Right? There are also questions of the PDF FRR. Then we are using the PDF. Then because
You're just only considering PDF up to a certain point.
it's also fine.
Oh,
Yeah.
okay. I get it.
So I have the probability of R being greater than 1 is 1 minus the probability that R is less than or equal to 1.
Pi R squared instead.
1 over what?
Pi R squared.
I don't think so. It's definitely 1 over R squared over 4 squared or something like that.
Yeah, it would be 16 over R squared.
R squared over 16 probably. Why is 16 over R squared?
Sorry.
Yeah,
R squared
something
over
to this
16.
effect. Something, right? Something
Yeah,
to this
that
effect.
would be the probability.
Of
at any given point.
one minus or this something like that. Yeah.
I mean like for it, PDF.
CDF is 4A, 4A. No. 4A I think is something to do with pi r squared over 16. This one, right?
As you increase.
For r squared over 16 for r being from 4 to 0, to be precise. Because this is actually pi r squared over pi 4 squared.
Yeah.
R squared over 16 is the CDF.
Yeah.
Or this CD, then you differentiate.
Yeah, because
Then we get another different thing. Then it's not 1 over 16 pi. Because we got a PDF 1 over 16 pi. Yeah. But then if we differentiate the CDF, we get another.
So this one cancels. This is the CDF FRR equals to this. Then if we differentiate to get FR, then we get R over 8, is it?
Yeah.
Then what's wrong?
But the other CDF we get is 1 over 16 pi. 1 over 16.
No, but these are different things. This is the CDF of, this is the PDF of R. The 1 over 16 pi is a PDF of XY.
But R is not the, isn't R the
R is the
function of
yes,
X and Y?
yes. The original PDF is 1 over 16 pi, where XY belong to the circle, right, of radius 4. This is f of XY, right? This is a different object than this is 0 otherwise. This is a different object than R. That's a XY thing. See two different things. One is the PDF of XY. Yeah. You agree with me? I haven't actually done this question, but I know it can be done.
Sorry, I was just correcting what I had down. I was wrong.
This is the PDF of X and Y. All right. The PDF of R, with R is a function of X and Y. All right. So this PDF may not be the same.
Oh.
This R actually, R goes from, what is the meaningful values of R is from 0 to 4. This one for this one, this is 0 otherwise. This is the PDF of R, this otherwise, okay?
Yeah, because each point would be more likely.
Yeah, if you go out, right, if this is uniform, right, then you go out, this outside is more likely, right? This outside part is more likely because there's more area here. Inside here is more less likely, right?
am I right to say like this one for this we don't differentiate one time to get this. But
yes.
For this one we have to like integrate twice in order to get the PDF of
Very, very carefully. Because this is a circle. Right.
Yeah,
Very, very carefully.
what we did was when we were discussing, we got here. Then we were looking at how, then we like, oh, we have to differentiate twice because we were looking at A as the
I see. But is it to get to R from here is very difficult? It's possible.
That's why we like that.
Yeah. I would rather you get the CDF here and then you differentiate one time. Finish.
Okay. Differentiate one time you get the PDF.
Yeah, I think this comparison, this is the small, the way I think about it is a small area divided by the big area.
Yeah,
Okay.
that's what.
Yeah, do circle. All right, then you can differentiate one time. That's it.
So we take that's whatever 16
I
and
believe so.
so we get that twice. Okay.
Once. Okay. Anything else?
For question 1 and question 4, they both have.
Actually, I have to go.
Oh.
Yeah.
You show him your
Triangle.
Yeah, it's a triangle. It's a triangle. Because this one is, I can draw it for you. It's like this one.
Y equals to 1 over
Like this one. Okay.
Okay. Thanks, bro.
Sure. This is not such a good time for me. I need to leave to pick up the kids. Yeah. Okay, take care, everybody.
Yeah.
I'm going to log off this.